I'm not gonna lie, attendance is a little bit better than I thought it would be today. I know there's only like five of you, but I was thinking about canceling class just because it's like Thanksgiving. But if I hadn't missed if I weren't on my trip like 2 weeks ago, I probably would have today. But anyways, I'm not even sharing my screen. You can't even see what's on my tablet. Anyways, we're just gonna, I mean, there's only really 3 more days of lecture in this class, including today. Like we have today's class, and then we're gonna have Monday and Wednesday next week, and then on Friday we're going to review for the final exam. So there's only 3 more days in which I can teach you new things.
So we're not meeting the rest of the week.
I am used to it's Thanksgiving break. Yeah, we don't have classes on Wednesday and Friday. We go at Thanksgiving break. Yeah, so I don't even know what I'm gonna do next week, to be honest. I think today we're gonna finish up probability, and then maybe next week we'll do finite state machines or something like that. I don't know. Maybe I should look at some application of probability just to stay in line. But yeah, I wanted to continue talking about probability a little bit because all the probability problems we've been looking at thus far have mostly just been looking at independent events and scenarios. So kind of also have to know like what if one event determines the next or has an influence over the next, or what happens if not every single probability is equally likely. And so this is section 7.2. Maybe we'll do more probability next week. Maybe not.
Think I, oh, I think I made I have wrote down some papers last night for
Yeah, we can talk about it later.
short assignment.
Yeah, and so there's a homework assignment due tomorrow night by 11:59. I mean, it's not due in class necessarily right now. And so the only thing you need to remember from section 7.1 is the definition of probability in the first place. So the two things you need to be aware of is there's the event space and then there's the sample space. So just as a reminder, the event space is really just the set of successful outcomes for the experiment you're running. For instance, if you're flipping a coin, you can have heads or you can have tails. If you're only interested in finding the number of heads that you have, your event space is just going to be the set of heads. And then the sample space is the collection of all possible outcomes. So if you're flipping a coin, it's going to be heads or tails. And so the probability is just the cardinality of the event space over the sample space. We did a number of examples last week, so this should be pretty familiar. And so last week we were looking at outcomes that were equally likely to one another. And this time we're going to be looking at experiments that could have outcomes that aren't equally likely. So for instance, I mean, I feel like I should move away from the example of a coin, but you could have a coin that's going to be biased. So that way it comes up heads twice as often as tails. So it has like a 2/3 chance instead of a 1/3 chance. Or if someone's like cheating at dice or something like that, they can have like a weighted die. Similarly, the likelihood that the input of a linear search in a particular list or is a particular, I'm pretty sure I should say, of a linear search in a particular element in a list or is not in the list depends on how the input is generated in the first place. So you need to know how to model the likelihood of such events in those situations. And so we go a little bit more general in terms of the mathematics here, in terms of how we're assigning probabilities. If you've taken calculus 2, you probably have done some work where you've calculated probability in terms of integrals. And usually you define some sort of like probability space in the following way. So we're going to let S be the sample space of an experiment with a finite number of outcomes. And for every single possible outcome, we assign a probability, P of S, to each outcome S. There's only 2 conditions that need to be met for this to be like a probability function. We have to have that P of S is between 0 and 1. This is just saying that we're assigning some percentage or probability to S, right? And a probability has to exist between 0 or 1. And then we have to have that if you take the sum of all possible outcomes, it ends up being equal to 1. So this is explained in the paragraph below. So condition 1 states the probability of each outcome is a non-negative real number, no greater than 1. And then condition 2 states that the sum of the probabilities of all possible outcomes should be 1. In other words, when we do the experiment, it has to be a certainty that one of the outcomes ends up occurring, right? If this didn't add up to 1, if it added up to like 0.9, I guess then you would have like a 10% chance that nothing happens, which is impossible. And so the first equation we'll look at involves conditional probability. And so conditional probability is the likelihood of an event E occurring given that another event F has already occurred. And so the way of thinking about this is we're kind of assuming that E exists within F. So you can treat F as if it's its own sample space. Like in order for us to care about E, it has to exist within F. So we're going to care about the intersection, and we're going to treat F as the sample space. So in general, to find the conditional probability of E given F, we use F as the sample space, and for the outcome E to occur, this outcome must also belong to the intersection of E and F. And so this will be the definition of conditional probability. So we let E and F be events where the probability of F occurring is greater than 0. And then the conditional probability of E given F is going to be denoted as the following. So it's like the probability, and then you have E, and then you have a vertical bar, and then F. And it's going to be defined as the following quotient. It's going to be the probability of E and F divided by the probability of F. So you might be thinking, like, how do I know when we have a conditional probability? Usually it's going to be given in the wording. So you have to read the problem and have some sort of interpretation that will tell you that it's going to be a conditional probability. So the next two examples, we're going to have to use this conditional probability equation, and I'll explain why after reading. So for the first example, we're given a bit string of length 4 is generated at random so that each of the 16-bit strings of length 4 is going to be equally likely. And so it's asking what is the probability that it contains at least two consecutive zeros, given that the first bit is going to be a 0 as well. So we assume that 0 bits and 1 bits are going to be equally likely to 1. So how do you determine that this is a conditional probability problem? Is the fact that we care about the probability of getting a 4-bit string that contains at least two zeros, but we only care about the situation where the first bit is going to be a 0, right? So it's conditional upon the fact that the first bit is going to end up being 0. And so usually how I like beginning these sorts of problems is I want to define what E is going to be, and I want to define what F is going to be as well. And so these are two events.
So we don't need to write anything about its birth rate.
No. So this is going to be the event. So E, this is the event you care about measuring, right? We care about the probability that the bit string of length 4 contains two consecutive zeros, right? So this is the event we care about, having two consecutive zeros. So this is the event where we have a bit string of length 4 has two consecutive zeros. Let me write it like this. Oh, I have space. Consecutive zeros. And then this is conditional upon the fact that the first bit is going to be 0, right? So it's given that its first bit is going to be 0. So this is the event that the first bit is 0. And so now if we want to find, so this is what it's asking, right? It's asking us to find the conditional probability of E, assuming that we have F occurs in the first place. So ultimately, we want to find this probability, E conditional upon F. And we know that this is equal to the probability of the intersection of the two. So it's the probability of E intersect F. And then you divide by the probability that F occurs. So there are a couple of things that we need to find, right? We need to find the probability of F. We need to find the probability of E intersect F. And so you can do this by doing some counting, right? So the probability of F, this is going to be equal to the cardinality of F divided by the cardinality of the total sample space. So the sample space here is the collection of all possible bit strings of length 4, right? And so if you do just a little bit of counting, you don't have to write out what the actual elements are going to be. Instead, you can just think, like, what does it mean for the first bit to be 0? It means that the first bit is decided, and then for the remaining 3 bits, you have 3 choices, right? You have 3 choices between 0 and 1 amongst the 3 remaining. And so that gives you 2 to the 3 choices, or 2 to the 3 possibilities. So we've done problems like this in the past, right? In section or in chapter 6. Right, so the cardinality of f will be 2 to the third because we have 3 choices of binary numbers for the last 3 digits. And then the total number of bit strings of length 4 is 2 to the 4th power. You have 4 choices for each digit, so that's going to be 2 to the 4. And so the probability of f is just going to be 1/2, right? If you do 2 to the 3rd power over 2 to the 4th power, it's just going to be 1/2. And then we also need to determine what E intersect F is going to be. This one's a little bit more complicated to think about in terms of just counting, like we were doing in chapter 6. This one, I would recommend just writing out what the elements are going to look like. So E intersect F means that the event, or means that the first bit has to be 0. And then it also means that we have to have 2 consecutive zeros. So you can have more than 2 consecutive zeros. You can have like 4 consecutive zeros or like 3 consecutive zeros, but you have to have at least 2 consecutive zeros, right? So you can have 0, 0, 0. It's like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. You can't move. Well, actually, you could move the one over.
Oh, is that like the start of a? Is that I thought that was 2? That might have had some um mistaken one on top of it, but is it actually start of a bracket?
Wait, what is this in reference of? Oh yeah, that's a set bracket. Yeah, so this is a set. So just like, yeah, so this is a set. You're taking the intersection of 2 sets, so you're gonna get a set back out of it. And then, so this is the set of E intersect F, right? You have to have a 0 starting, and then you have to have 2 consecutive zeros that show somewhere in the string, right? So there's 4 consecutive zeros here, 3 here. You have 2 consecutive zeros here, 2 consecutive zeros here, and then 2 consecutive zeros here. These are all the possibilities that one could possibly have. And so then the probability that the intersection occurs, this is going to be the cardinality of the intersection, which we just found. I mean, it's a 5-element set, so the cardinality is equal to 5. And then you divide by the cardinality of the sample space. So the total number of 4-bit strings that you can have. And so this is going to be equal to 5 over 16. And so now we know what both of these numbers are, right? We know the probability of E intersect F. We know the probability of F. And so now it's just a matter of dividing the two, right? So the probability of E intersect F was 5 over 16. And then the probability of F was equal to 1/2. So this is 5 over 16 over 1/2. And so this is equal to 5 over 8. Right. So assuming the first bit ends up being equal to 0, the probability of getting at least 2 consecutive zeros is going to be 5 over 8 total. So that's the answer for this one. And again, where you're kind of thinking in terms of this like conditional probability is really this word given, right? This is the operative word that tells you that you should be thinking in terms of conditional probability. Care about one thing given something else happens in the first place. Any questions about this example? Okay, yeah, the next one, it's a little bit similar, or at least, I mean, it's going to be a probability problem, of course. So we care about right now, but the context is going to be a little bit different. So for this example, it's asking what is the conditional probability that a family with 2 children has 2 boys given they have at least one boy in the first place. And so we assume that each of the possibilities, so there's four possibilities total, right? You have boy, 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 girl, girl, boy, or girl, girl. We're going to assume that they're going to be equally likely, where we have that B represents a boy and then G represents a girl. And then order matters in the sense that it's going to denote the age or the order in which the birth occurs. So we can have that boy girl represents a family with an older boy and a younger girl. So it's kind of like the boy was born first, the girl was born second. While girl boy represents the opposite. So older girl and then younger boy. And so I'll just write out first like the sample space. I didn't write out the sample space before, but the sample space is every single possible combination of, I guess, gender of like the two children that you have. So it's going to be given by 4. So the cardinality of the sample space here, this is going to be equal to 4. Maybe I should write it out like this. This is like boy, 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 girl, girl, boy, and then girl, girl. So this is the sample space. The cardinality is going to be equal to 4. And then the two events that we care about, right? So how do we determine that this is a problem that involves conditional probability? So we're assuming, well, I guess it says what is the conditional probability, but maybe you're not always going to be told that. But we're said like what we care about is we care about a family with 2 children that has 2 boys, given that they already have at least one boy, right? So the thing we care about is the family. I guess this event space or this, yeah, the event space E is having 2 children, both of which are going to be boys. So we have E here. This is the event. The family has 2 boys. And then F is really the event that the family has at least one boy. Right. So it's really in how it's written, right? Again, it's this word given, right? One event given another event has occurred. It's kind of the signifier that you should be thinking in terms of conditional probability. And so what do we care about here? Again, what we ultimately want to find is we want to find the probability of E given F. This is given by the probability of the intersection of the 2 sets divided by the probability of F. So again, we need to find the probability of these 2 events. And so the first event or the first thing we'll think about is the probability of the intersection. And the probability of the intersection is really just equal to the probability of E, right? Like if you think about the intersection of E with F, F is the event that the family has at least one boy. E is the event that the family has 2 boys. If you take the intersection, you're really saying the family has at least one boy and it has 2 boys, which is really just the same thing as saying that it has 2 boys, right? So the probability of E intersect F, this is the cardinality of E intersect F divided by the cardinality of the sample space. We know the cardinality of the sample space, this is equal to 4. And then E intersect F is the event where the family has 2 boys. There's only one possibility where this occurs, right? That's just when you have BB, right? If you have BG, GB, or GG, that means you don't have 2 boys. So the only possibility for E intersect F is having BB. So the cardinality of E intersect F is really the cardinality of the set just consisting of BB. So this is equal to 1 over 4. Let me shrink this part down so a little bit more writing space. And then we also care about the probability of F. So the probability of F is just saying that the family has at least one boy. And so the only thing you need to exclude is the girl-girl situation. So that should give you a probability of 3 over 4. But to write it out more formally, this is the cardinality of F over the cardinality of S, where F is the set where you have boy, 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 girl, and then girl, boy. And then this is going to be over 4. So this is equal to 3 over 4. Right, so these are the two probabilities you're going to use to find the conditional probability. Right, so the conditional probability is the probability of the intersection, which was equal to 1 over 4. And then it's going to be divided by the probability of F, which was given by 3 over 4. So what happens is if you do 1 over 4 divided by 3 over 4, I don't know if people have had much exposure to this. This is the same thing as doing 1 over 4 multiplied by the reciprocal of the fraction you have in the denominator. So this is times 4 over 3, which is equal to 1 over 3. I wasn't sure if people have had a lot of experience with that, but you end up getting 1 over 3 here. This is a general rule. Maybe I don't need to write this out, but in case you haven't seen it, if you do A over B divided by C over D, it's the same thing as having A over B multiplied by D over C. In case you get confused by like fractions over fractions, this is the rule that you always want to follow. Right, maybe I don't need to say it, but just in case you're confused about where this 1 over 3 came from at the end. Any questions about this example? Okay, so those are just two examples where we're looking at conditional probability. I'm not going to go much harder than that. The next thing I care about is going to be independence. So this was the context we existed in section 6.1 or 7.1 last week, where we assumed the events were independent or didn't influence one another. Right, so like the two events we were looking at in the previous examples, one event influenced the other. That's why we had to care about conditional probability. So we want to be able to determine when two events are actually independent from one another to make our lives easier and to make calculations nicer. So independent events are two or more events where the outcome of one has no effect on the probability of the other. So like the classic example that I keep going to is the flipping of a coin. If you flip the tail, like if you flip tails, it has no impact on what the next flip is going to end up being. And so the outcome of the previous flip has no influence on the outcome of the next flip. And so this is the definition of two events being independent of one another. So the events E and F are independent if and only if we have that the probability of the intersection of E and F ends up just being equal to the product of the two probabilities, right? So if you take the intersection, it ends up just being the probability of E times the probability of F. And so we'll look at maybe one example of this, maybe two examples. I kind of like the next page. I might skip one example here. All right. So for this example, it's again looking at generating bit strings, and then the next example is looking at families. They have you want to count like the number of boys or something like that. So this first example, we're supposing it tells you what E and F are going to be. So we suppose that E is the event that a randomly generated bit string of length 4 begins with a 1, and F is the event that this bit string contains an even number of ones. And so what it's asking is it's asking if E and F are independent if the 16 bit strings of length 4 are equally likely to one another. So you could think through this, I suppose, and determine whether or not they're independent just from how they explain things. But the rigorous way of doing this is proving that these two equations are equal to one another. So we're going to find the probability of E intersect F, and we want to show that it's going to be equal to the probability of E times the probability of F. Right, so again, we're in this case where we're looking at bit strings of length 4. So the probability of the sample space, again, we have two choices for each bit that we have. So that gives you 2 to the 4 choices. So this is going to be 2 to the 4th power. So this is going to be equal to 16. It's the cardinality of the sample space. To find the probability of E and F, we have to make use of this cardinality. So next we're going to find the cardinality of E. So again, E is the event that a randomly generated bit string of length 4 begins with a 1. And so what we're saying is that we're choosing we don't have any choice. The opposite of choosing. We don't have any choice on what the first bit string is going to be. We're always assuming it's going to be 1. That gives you 3 choices for the other bit strings that you can have. So that gives you 2 to the 3 total possibilities. And so this is equal to 8. And so this means the probability of E, this is equal to the cardinality of E divided by the cardinality of S. This is equal to 8 over 16, which is equal to 1/2. So we know the probability of E, or the probability of E is equal to 1/2. We'll make use of that later on. And then we also care about F, right? So F is a little bit harder to think about, I would say. Right? So F is the event that the bit string contains an even number of ones. So that means you can have 0 ones. 0 is an even number because it's 2 times 0. So you can think about the case where you have 0 ones. You can think about the case where you have 2 ones, and you can think about the case where you have 4 ones. And so one way of thinking about this or counting this is by using combinations, right? In the sense that a bit string of length 4 is really just a collection of, it's like a subset of 4 elements in a sense. And we want to find a subset consisting of an even number of ones. So you could do that. What you could do is you can write this out as being 4 choose 0, right? This corresponds to having a bit string where there's 0 ones in it, plus 4 choose 2. This is the number of bit strings that have 2 ones inside of it. And then this is going to be plus 4 choose 4. This is the number of bit strings that have 1 or 4 ones in it, right? So 4 choose 0, this is equal to 1. 4 choose 2, we calculated this last week, it's equal to 6. And then 4 choose 4, that's equal to 1 as well. So this ends up being equal to 8. And so maybe I'm not going to label all of them, but just as an example, so this is the number of bit strings with 2 ones. And then analogous, this is like the number of bit strings with 0 ones, number of bit strings with 4 ones. So you can do this in terms of combinations. And generally you want to do that. You don't want to like write out a set with like 8 elements in it if you can count it and using other means. And so what this means, again, the cardinality of E was equal to 8. The cardinality of F was equal to 8 as well. So just like we had before, the probability of F, this is just going to be equal to 8 over 16, which is equal to 1/2. So the probability of E and the probability of F, they're both equal to 1/2. Now all that's left to determine their independence from one another is we need to find the probability of E intersect F. And so for this one, I don't know, there's probably a way of counting it, but I'm just going to write out the elements of the set. So we have the intersection of E with F. It's going to be the following. So you can have, well, you have to have at least one for it to be an E and F. So we don't have the case where we have 0 ones in it. When we have 4 ones, that means you have an even number of ones and you have a 1 in the first entry, or whatever you want to call it, the first bit. So that'll be 1 1. Like that's going to be in the intersection. And then the others will be 1 0 0 1, 1 0 1 0. And then you have 1 1 0 0. Oops, 1 1 0 0. Right. So you have to have a 1 for the first bit in order for it to be an E. And then for it to be an F, you have to have an even number of ones. So these are the 4 possibilities that you have. And so that means that the probability of the intersection, this is going to be equal to 4 over 16, which is equal to 1 over 4. And so now the key observation here is if we want the 2 events to be independent of one another, that means that we have to have that the probability of E intersect F is equal to the product of the probability of E and the probability of F. And you can notice that you have 1/2 times 1/2 is equal to 1/4, right? But to write it out more formally, this is kind of the concluding statement. We have the probability of E intersect F. We found that this is equal to 1/4. And we know that 1/4, this is equal to 1/2 times 1/2, where we know that 1/2 is equal to the probability of E. So this is equal to the probability of E times this other 1/2, which is equal to the probability of F. So we've just shown that the probability of the intersection is equal to the probability of the product, or I should say the product of the probabilities. And so that means that they're independent of one another. They're two independent events. So maybe I should have one little line squeezed in here at the bottom that the events are independent. Okay. Any questions about this example? Yeah, you should be noting, like there isn't really anything new in terms of the computations we're doing compared to what we did in section 7.1. We're really just doing the same computations we did last week, except now at the very end, we're comparing one equation or one probability to the other, right? So if you understand section 7.1, it isn't that much of a jump to understand 7.2. That's what I'm getting. Any questions about this one before moving on? Oops. Okay, next one. I don't know. I kind of want to skip this one. We can go through. I feel like it's important to go through one more question for independence, and then plus, and the more time I spend on this, the less notes I have to write for next. So this next example, I think it's good to do one more example of independence. So this is similar to the one we did before, right? Where we're looking at a family, except instead of having 2 children now, they're going to be having 3 children. So we're going to be asking the question, are the events E, that a family with 3 children has children of both sexes, and F, the event that this family has at most 1 boy, going to be independent of one another? And then we're going to assume that the 8 ways a family can have 3 children are going to be equally likely to one another. Okay, and so just like we've done for the previous problems, the first thing we're going to do is write out the sample space, or not write out the sample space, but at least count out the cardinality of the sample space. All right, so the sample space here is just all possible combinations of having 3 children. So if there's 3 children you're having, it means there's 2 possibilities, at least like they're assuming there's 2 possibilities for each sex that you can have. So that gives you 2 to the 3 possibilities, which is equal to 8. So there's 2 to the 3, which is equal to 8 ways. Well, 8 ways to have 3 children. And then we need to think in terms of, like, we want to determine whether or not the events are independent of one another. And so again, we need to determine the probability of E, the cardinality, or probability of E, probability of F, and then the probability of the intersection. And we want to see if the product of the probabilities is equal to the probability of the intersection. And so first we'll focus on E. So E is the event that a family with 3 children has children of both sexes. There's only 2 situations in which you have to exclude. You have to exclude the situation where you have 3 boys, and then you have to exclude the situation where you have 3 girls, right? And then all the other outcomes are going to be valid, right? So the cardinality of E is really just going to be equal to the cardinality of the sample space subtracted by the cardinality of the set where you have all boys and then all girls. So it's really the complement of the set where the children have the same sex, right? And so this is going to be equal to 8 minus 2, which is equal to 6. And so this implies that the probability of E is going to be equal to 6 over 8, which is equal to 3 over 4. Right, so the probability of E is going to be this 3 over 4. And then the probability of F, what was F? F is the event that the family has at most one boy, right? So that means you can have 0 boys as well. It's really the same as saying you have like 2 or more girls. It's like an equivalent way of saying it. So I'm just going to write out what the set is going to be. So this is the cardinality of the set where you have at most one boy. So you can have 3 girls. And then you can have like girl, girl, boy. You have girl, boy, girl. Or you can have boy, girl, girl like this. Right? So you can have all girls or you can have 2 girls, and then it's a matter of like the age or the order in which like the births happen, I suppose. And so you have 4 elements, and it's an 8-element sample space. So in total, that means the probability is going to be 1/2. So the probability of F is going to be equal to 4 over 8. So this is going to be equal to 1/2. And I guess I should have, I mean, you can count, but this is equal to 4, right? It's a 4-element set. So the probability of F occurring is going to be 1/2. And so if the events are going to be independent of one another, if we take the intersection of these two sets, it should end up being equal to 3 over 8. Right, so the intersection of the two events is going to be saying that you have to have at most one boy, and you have to have a child of both sexes, or you have to have children of both sexes. I don't know how to word that correctly. And so E intersect F here, or rather the intersection, like the cardinality of the intersection, it's really just going to be F over again, except you exclude the case where you have 3 girls, right? So this is going to be equal to the cardinality of a set where you have girl, girl, boy, girl, boy, girl, and then boy, girl, girl, which is equal to 3, which implies that the probability of the intersection is going to be equal to 3 over 8. Which is kind of what I was saying before, right? For these to be independent of one another, you have to look at their product, and it should be equal to 3 over 8. So in conclusion, we have the following. So I mean, oh my God, you can already see that the events are going to be independent of one another, right? Because if you take the product, it's going to be equal to 3 over 8. But just to formalize it, we have that the probability of the intersection, this is equal to 3 over 8, which you can write as being equal to 3 over 4 times 1/2. For the 3 over 4, this is equal to the probability of E, and this 1/2, that's equal to the probability of F. And thus, we have that, or I can't read that. So that's thus, we have that the events are independent. Right, so again, we're not doing anything new. This is really just the content from 7.1 over again, except now we have this little check at the end. So as long as you can do the probability techniques from section 7.1, you can do this problem or like problems of this nature. You just have to do this little check at the end. Any questions about this example? Okay, so I can maybe spend, let's see, what can I cover here? Maybe I can do the next page, or at least the first part of the next page, and then we can continue next week after you've forgotten everything due to the break. Maybe that's not the best way of doing things, but I don't know. I'm just gonna go through it anyways. And so we're gonna look at one example of a distribution. We're gonna be looking at something called a binomial distribution, which, as you should expect, is going to involve something involving like binomial coefficients from chapter 6. And so where is this going to show up? So we're going to suppose that an experiment can have only two possible outcomes. So for instance, when a bit is generated at random, the possible outcomes are either going to be a 0 and a 1. Furthermore, when a coin is flipped, the possible outcomes are going to be a heads or a tails. So each performance of an experiment with two possible outcomes is going to be called a Bernoulli trial, after James Bernoulli. And so in general, possible outcomes of a Bernoulli trial is going to be called a success or a failure. So we're going to label P as the probability of a success and Q as the probability of a failure. So you only have two outcomes, so you can label one as success, the other as failure, depending on what you're trying to measure. And then we should have that the sum of P and Q should be equal to 1, right? Like if you're flipping a coin, it's either going to be heads or tails, so the probability of the two should add up until 1. It wouldn't make sense if you're flipping a coin and they only added up to 0.9, because that would indicate that you can, I mean, it could land on its side, I suppose, but I don't know if that doesn't, you don't really account for that, I suppose. All right, so many problems can be determined or solved by determining the probability of k successes when an experiment consists of n mutually independent Bernoulli triangles. So assuming all of our events are going to be independent from one another. And so what does it mean to be mutually independent? It's mutually independent if the conditional probability of success on any given trial is p, given any information whatsoever about the outcomes of the other trials. I wouldn't worry about it too much. You don't have to know what mutual independence means. And so I guess I'm going to prove the following theorem, and then we'll apply it in a couple of examples next week. And so this is the theorem that illustrates everything you need to understand about these Bernoulli triangles, or not triangles, trials. For some reason, I want to say like Bermuda Triangle. I don't know why. When I see Bernoulli trial. So the probability of exactly k successes in n independent Bernoulli trials with probability of success p and probability of failure q minus p. Oh, it shouldn't be q minus p. It should be 1 minus p. This should be, instead of q minus p, it should be q is equal to 1 minus p. Is given by the following, right? So again, this C of nk, this is k combinations of a set of n elements. So you could write it out in the following way. This is the same as doing n choose k times p to the kth power and then q to the n minus k. You should be thinking this is kind of like our binomial coefficients, right? Like if you think in terms of the binomial theorem we talked about last week, this is almost like we're doing like p plus q to the kth power or something like that, or not kth power, the nth power. This would be one of the, like the coefficient of like this specific power. So it's like there's like some relation. That's why they call it the binomial distribution. It's kind of like the binomial theorem. And so how would we prove something like this? A lot of it's just going to be put in words pretty much. Like you want to explain where these terms are going to be coming from, and then you want to relate it to the actual probability of what's happening. So it's not really that mathematical. It's more interpretive. And so we're going to be assuming we have n trials. So when n trials are carried out, we can look at the set of all possible outcomes. So the outcome is an n tuple, which we can label as like T1, T2 up until Tn, where these are all going to either be failures or successes. So like T1 can be a success or a failure, T2 can be a success or a failure, Tn can be a success or a failure. We're going to be assuming, well, this is exactly what I just said. So we have Ti is either equal to S, which indicates a success, or we have that Ti is equal to F, which indicates a failure. For every single index that we have. So the probability of k successes And if you have k successes, it must mean you have n minus k failures because it's either a success or a failure. And we have n trials. So that means we're going to have n minus k failures. This is going to be given by p to the kth power and then q to the n minus k power. And then you need to think about all possible, I guess, like orderings or situations you can have for these various outcomes that you have. And so where does this binomial coefficient come from? Where does n choose k come from? So as there are n choose k, n tuples of successes and failures containing exactly, sorry, it's a lot of writing. I don't know how else to really, I could have written a more condensed version, I suppose. Exactly k s's, right? So this is where the binomial coefficient's coming from. Like you have a set of n elements and you want to find a subset consisting of k successes. So you're going to have n choose k such situations. This tells us that the probability, hence the probability, is going to be this n choose k times p to the kth power times q to the n minus k. And before I leave, I know I'm kind of like quickly going through this. So that's where this equation comes from. I'm not going to ask you to prove stuff like this on the exam, but you'll have to maybe like write this on a note card and apply it for a problem or something like that. So just as like a quick example before I end class, is we have the following. So a coin is biased so that the probability of heads is 2/3. It then asks, what is the probability that exactly 4 heads come up when the coin is flipped 7 times, assuming that the flips are independent of one another? So you really just plug into the equation we have here. So we have n trials total because we're flipping the coin 7 times. So we're going to have 7 choose something. So here we're going to define success as heads coming up exactly 4 times. So we're going to do 7 choose 4 because we want 4 heads. And now it's going to be the probability that heads happens. So that's going to be 2/3. And then we want k to be equal to this 4 here. So it's going to be 2/3 to the 4th power. And then the probability we don't have heads is going to be 1 minus 2/3. So that'll be 1/3. And then we want 3 tails to happen. So that's going to be to the 3rd power. And so this ends up being equal to 560 over 2,187. Right. So if you know the formula and you know what to apply and where to put it, like these problems are pretty straightforward. So just to be clear, n here was equal to 7, k was equal to 4. Sorry, my handwriting's very bad today. We have p is equal to 2/3, and then q was equal to 1/3. Maybe I should have written this out before plugging into the formula, but I wanted to make sure I had enough time to actually go through the problem. Right, so next week, I mean, you'll probably forget most of this over the week, but I'll go through 2 more examples of using this formula that I just explained. But yeah, that'll be the end of class. Again, we have break this week. I don't need to tell you. We don't have class on Wednesday or Friday, so this is where we'll pick up next week. Oh, and I also have some old homework and quizzes, or really a whole like old homework and a quiz. So if you want to pick it up, you can stop by.
Does that say R equals 4 or B equals 4?
At the bottom, or where?
Or if it's a K?
Oh, it's okay. Yeah. Let me just sit through this. Yeah. Oh, yeah. Is that it? Yeah. Yeah, I have the exam in mind. Here's the. Oh.
May I provide you with my homework?
Oh yeah, now you can turn in your homework now.
We don't meet each other tomorrow.
Yeah, but you can slide it under the door.